Hey folks, thanks so much for joining me today and sticking around towards the end of our session to learn about detecting potential threats to your containers. Let me introduce myself. My name is Tim Peacock. I'm a product manager here in Google. I work on our cloud security threat detection products. So everything within Security Command Center that comes down to finding when bad things are happening in your environment, whether that's event threat detection or container threat detection, I'm the product manager responsible for those features. Today, we're going to be talking about container threat detection and what are containers, what is container security, what are some of the things that Google does in the container security space to help keep you safe, and specifically, what are we building with container threat detection to detect threats in containers at runtime. So I thought it might be good for the security folks in the room to start with, well, what exactly is a container? Now, containers have been around for a number of years now, but I find it's helpful to set some level expectations here. So while we think of them as all the rage, they've been around for a long time, and you can think of them as part of an evolution from bare metal to virtual machines to containerized environments. And so, when you're in a bare metal world, you've got to worry about hardware, application dependencies, and eventually your business specific application code all the way at the top. Moving to virtual machines like a GCE instance, well, that abstracts the hardware. But when you get into the container world, we actually give you a really nice mechanism with containers for shipping your application code and its dependencies in a way that's robust, immutable, and in GKE, Google Kubernetes Engine, you don't have to worry about the operating system or the virtual machines that you worry about. So you spend your engineer's time worrying what really matters, which is about your application and business logic specific code. So there's nice things about containers for the security practitioners in the room beyond the application engineers. First off, containers are generally deployed in ways which are extremely short-lived, so that your patching can be virtually instantaneous, and you can constantly be patching vulnerable dependencies in your code. Containers, when run in Google Kubernetes Engine with our recommended container optimized OS, which we talk about in a little bit, costs, containers are fundamentally immutable. So anytime you see a change happening in the file system or unexpected behavior there, you have a really strong signal that something unusual and unexpected is happening in your environment. With GKE, we make it really easy to deploy good security defaults so that you have configuration as code, so that your configuration is deployed, checked in, and your security defaults and best practices are baked into how things are running. And finally, with a lot of the container isolation that we're working on in Google Cloud, you get a lot of increased security and stronger boundaries between different pieces of code and different parts of your application without a lot of stress for your developers. So there's a lot of great security advantages to containers, but what is container security as a class of problems? Well, we think about container security really in three pillars. First, is my infrastructure secure for developing containers? Do I have the right systems in place to protect my secrets? Is my network secure? Am I using the right logging functionality when it comes to things like deploying my containers? Which brings us to software supply chain. This is the question of, do I have the right frameworks in place and the right build systems, the right scanning systems to make sure that the workloads I'm deploying and the dependencies I'm pulling into those deployments are those vulnerability free? And when there are vulnerabilities, do I have a robust system in place for making sure that those vulnerabilities are assigned to owners, that patching timelines are tracked, and that I'm able to make sure that the code I'm deploying is secure from the get-go? And then finally, in that software supply chain problem, how do I make sure that between the time that something is built and the time that something is deployed, how do I make sure that the code that gets deployed is the code that I built? And so with things like Google Container Registry vulnerability scanning, we help solve the first problem. And with things like binary authorization, we help solve the second problem. So you know that what came out of your build system is what went into production. And you're guaranteed that the only things going into production are things that were signed by your build system. That's all great for the moment that things become alive, but what happens once things are running? How do I quickly identify a container that's acting suspiciously? What actions can I take to protect my environment? And how can I scale that across my entire estate of containerized workload with as little DevOps impact to DevOps teams and as little overhead for security teams? In each of these pillars, there are different threats we can worry about. In infrastructure security, we can worry about privilege escalation. Does an actor who gets into one place have the ability to get into another place? Are there credentials floating around in places that they shouldn't be? Is there use of the Kubernetes API in ways that we don't want to see it used? And are there users who are overprivileged for the jobs that they need to do? On the supply chain, like I was saying, are there vulnerabilities present that should have been patched a long time ago? Is the supply chain itself vulnerable to attack by a malicious outsider? And are there common libraries that are vulnerable to exploit? And then when it comes to runtime, the threats we really care about are workload compromise and exploit, and then container escape and pivoting into the rest of your cloud environment. Because when it comes to container security, once your containers are part of your cloud, you need to make sure that the attack focused on your container is not just an attack on your container. You need to make sure that that doesn't then become a compromise of the broader cloud environment. At Google, we've done a lot of work to help you protect each of these pillars and have systems and products in place to protect you at each stage of the container security lifecycle. So there's a couple of things that are baked into the platform. We have best practices on by default, a disabled Kubernetes dashboard, for example. We have our up-to-date hardening guide. We have the CIS benchmarks for GKE security that we worked with the CIS Foundation to publish and make available to users. The container optimized OS is an operating system that's been stripped down, hardened, and has an immutable file system so that you have the fewest things for an adversary to take advantage of or get their hands on when they compromise a workload in that environment. With Node Auto Upgrade, we're able to automatically update your Kubernetes version, including security patches, so that your teams don't need to worry about what infrastructure they're running on. They, again, just focus on that slice at the top of the stack. What's their business logic? What's their application code? And let Google handle the problem of patching Kubernetes and taking care of any issues or vulnerabilities that crop up there. On the supply chain, we have container registry vulnerability scanning, which is a feature within our Google Container Registry product that automatically inspects your images and looks for vulnerabilities present there at build time. This way, you're automatically alerted to potential CVEs inside your code before it can go into production. With binary authorization, like I alluded to earlier, not only are you able to see what vulnerabilities are present, you're able to declaratively say, only code that comes out of my build system can run in my production environment. And that can be run in both enforcement mode as well as an alert mode. And finally, for managed base images, you have common distributions patched automatically by Google. So that leaves us with the final pillar, runtime security. And that's what I'm here to talk to you today about, is really what are the things that we can do at runtime to detect when an adversary might be attacking or getting into one of your containerized workloads. So the product, appropriately enough, is known as Container Threat Detection because at Google, we love our descriptive names. And we thought, what could be more descriptive than saying threat detection in containers? And now you'll sometimes see this abbreviated KTD. The reason is to disambiguate it from any other kind of threat detection in cloud. So we call it Kubernetes KTD, Container Threat Detection. And what you get with Container Threat Detection is a managed service to detect threats in runtime with your containerized workloads. And it's really composed of several parts. We have a managed deployment service to take care of getting our instrumentation onto your clusters. We have an LSM that we baked into the Container Optimized OS or COS kernel, so a Linux security module designed specifically for detecting container-specific attacks, is embedded in all of the current versions of the Container Optimized OS. We have our daemon set, which we manage the deployment of, and then we have a detection plane that we run in the backend that communicates with the daemon set in order to actually do the heavy lifting of security decision making. So we use as little on-container compute as possible. So how does it all fit together? For a security team, it starts out with declarative control over where you want to have KTD's protection present. So you as a security team member would go into Security Command Center's control panel, say, I want to protect these clusters and not these clusters. We take that as a cue to go into those projects and with your permission that you've delegated to a service account, deploy our daemon set and activate our APIs. Our daemon set, when it's deployed to the cluster, wakes up the LSM, says, hey, LSM, please start giving me signals. And then it's responsible for not just taking those signals, but also becoming container aware and saying in which namespace did these signals originate, so that when we do detect a threat, we're not only able to tell you, hey, something bad happened on this cluster, we're able to tell you exactly which container that threat happened in the context of. And then finally, all of those findings end up in two places. While we write them to Cloud Logging as logs to make it easy to export them to on-prem systems or out to BigQuery or into Google Cloud Storage for long-term retention and archive, the primary place we expect users to be consuming our findings is again within the context of Security Command Center. Security Command Center is the single pane of glass, and I owe myself $1 in my security swear jar for using the phrase, but it's our central pane of glass for viewing data in Google Cloud about misconfigurations of your cloud assets, compliance violations, as well as all of the output of our runtime threat detection offerings, whether ETD, KTD, or other threat detection systems that we may or may not be working on in addition to those two. So what does this multi-tiered approach to threat detection get you? Well, first, it gets you kernel level visibility and monitoring from our LSM. So we operate the base layer of our detection from a very privileged standpoint, where we're able to make really great observations about what's actually happening. With the daemon set, we become container aware and have a secure communication path from LSM to our backend, so that we know the signals we're receiving come from systems that we deployed, not systems that an adversary has deployed. And finally, with the detection plane running in the backend, we're able to do the heavy lifting, whether it's machine learning powered, whether it's deduplication, or whether it's just security decision making without using memory or compute on your endpoints. So the system has been designed to be both robust to adversarial tampering, it's been designed to have kernel level visibility, and it's been designed to operate in a way that uses as few of your resources as possible while putting the burdens for management and upkeep and maintenance on us. So we take care of things like updating daemon sets, making sure that daemon sets are alive, and deploying them in the first place. So you as a security team have the benefit of deploying protection without having to hassle application owners to keep YAML files up to date with the latest version of whatever other daemon set you might have considered deploying. So what are we looking for today? Well, we're looking for three things today, and we're going to see in the demo in a little bit exactly how that works. But I want to give you a little bit of philosophy about why we're looking for the things that we're looking for. Rather than try to compete in a checkboxing war of this detection versus that detection, KTD is taking kind of a different approach informed by our kernel level visibility and our understanding of what's good and bad in GKE generally. So what we've attempted to do with our first set of detections here, added binary executed and new library linking, is to foreclose adversarial pathways in getting execution of files which were not part of the container when it was built. In other words, rather than detect individual pieces of malware or individual exploits, we're looking for broad classes of behavior that indicate an adversary has managed to get his or her payload onto your endpoint. And so what this gets us is robust detection of the addition of malware to a cluster that you own without your SOC team having to understand the difference between a million different types of findings, and instead puts them in a position of focusing on, well, what really got executed, not how did it get executed? Because regardless of how the file got there, we're going to pick up when it got executed. Finally, we're also detecting reverse shells from clusters to the internet. And this is another signal that an adversary has gotten control of a workload and has managed to phone home one way or another. So with these, what we're doing is foreclosing adversarial pathways. So we take away the ability of a bad guy to execute new code on your cluster, and we take away the ability of the bad guy to phone home and open up an interactive session. Now, we've got additional detectors that are coming later this year, and while I will simply tease the categories that they're coming in, we're interested in two additional areas. One is, like I said, catching the pivots from containers to the rest of your cloud environment. And we believe we're uniquely well positioned to do that given our relationship with the rest of Google Kubernetes Engine as a team and the rest of Google Cloud. And then secondarily, we're looking at a couple of really exciting machine learning powered detectors that I'm on the cusp of being able to talk about. And it hurts the soul of me as a product manager not to be able to talk about them today, but I promise we'll be able to talk about them really soon. And here we're leveraging Google's expertise in machine learning and our access to really special data sets in order to build detectors that we believe are uniquely powerful when it comes to detecting other classes of adversarial behavior. And so more to come soon, both in terms of detecting pivots out of compromised workloads, as well as using machine learning to detect compromise of your workloads. Now, I said there would be a demo, and there is. And so before I run the demo, I want to tell you what to expect with the demo so that as I'm going through it, you're not getting lost. The first thing we're going to do is we're going to look at a GKE cluster. And I actually launched it ahead of time. It was one of those, baking show tricks. We've got a GKE cluster running, and I'm going to show you that KTD is present on that cluster. I'm going to then deploy a vulnerable container, attack that container, and show you the findings that are generated in Security Command Center when I attack that container. So we'll go from having a cluster, deploying a container, attacking it, and seeing the results, all by the time you're done watching this video. So let's get started. Now, I've gone ahead and created a GKE cluster, and we're up and running. Now, I want to make sure that KTD, Container Threat Detection, is present on the machine. So we're going to make sure that it's there. And we can see, indeed, our Container Watcher daemon set is running, and it's been there just for a little while now. So the next thing we're going to do is we're going to launch a vulnerable Drupal image to this pod. All right, we've created our vulnerable Drupal service, and we're just going to make sure that we are getting that up and running. So we're going to curl it, just grab the head of that, and you will see that we've got very friendly Drupal stuff running here. Everything looks good with that. We're going to kill that, port forward now, and move on with the rest of the demo. So we're going to need the IP address of that Drupal service so we can attack it with Metasploit. And so we see that this Drupal cluster has this IP here. And now we're going to start up everybody's favorite attacker toolkit, Metasploit. So here we go. I'm going to wait for that to spin up. Now, this is a pretty common attack scenario where an adversary finds an exposed service on the internet and uses a nice automated tool like Metasploit to find what might or might not be vulnerable there. Now, in this case, we didn't actually expose any IPs to the internet. It's all happening locally. So you'll see that the addresses we're using are all RFC 1918 space, but the theory of the attack, the method of the attack, and the theory of defense remain the same, regardless of how the deployment is working. So we're going to give Metasploit just a second here to get going. All right, so we've got Metasploit up and running, and we're just going to grab its IP address for use later on. So there we go. And now we're going to start the Metasploit console. So here we go. I'm going to make this a little bit bigger. We're going to use that IP address that we grabbed earlier for the Drupal pod. In this case, 1047.248.125. We're going to set the IP address for Metasploit on this. And now Drupal, it turns out there's a number of different ways we can attack it, but we're going to go this way. And we're going to drop Meterpreter onto our vulnerable cluster. And let's run it. All right, so let's upload Nmap to our now exploited host. And let's open up a shell on the host. And let's see, who am I? Well, I'm running as www-data. So I've popped into a non-privileged user here in this compromised container, but I think that there's still quite a bit of opportunity for us as an adversary to, explore, see what we can do. So we're going to move over to temp. We're going to untar Nmap that we uploaded just a second ago. And now we're going to use Nmap and go for a little scanning activity. How does that sound? So here we go. We're going to run Nmap and scan our space. All right, and now having done that, let's exit out of all of this and see exactly what we detected over in Security Command Center. So here we are inside the dashboard for Security Command Center, and we're just going to pop over to the findings and see what we found thanks to our kernel level instrumentation, our user space daemon set, and our plane in the back end detecting everything that's going on. So let's first have a look at this added binary executed finding. Now we're going to dig into the details and see what we've got. Now this was detected 2 minutes ago, which is exactly when it ran, 2 minutes ago. And we're going to expand the source properties and see exactly the kind of detail that an analyst would have when understanding one of these threats. So at the very top, you're able to see a binary that was not part of the original container image was executed. It's a possible sign that an attacker has control of the workload and that they're executing arbitrary commands. Well, the first thing we tell the user is what exactly was pulled here. And so in this case, it's a Drupal version, and you've got the version information as well as a SHA. We've got the namespace, details about when the container was created, all of the environment variables that give us some context on what's going on there. And then if we keep scrolling down, we can also see exactly what binary was executed, its ID, what container it was in, what pod it was in, and some other information about when it happened. Well, that's all well and good, but it doesn't give the analyst a whole lot to go on. So what's the second finding that we dropped here? Well, this finding I think is going to be a little more recognizable to a lot of you, because this is the one where you can see in the process arguments that it was Nmap running and exactly what the adversary was up to. So with KTD, you get this kind of very close to real-time detection. You're able to see that this was detected a minute ago, which is how long it took me to tab over and start talking about it. And you get a whole ton of context about the environment in which it executed, the container that was involved in the attack, as well as the environment variables that were happening when this attack happened. So what you saw was the deployment of a cluster, deployment of a vulnerable workload, use of Metasploit to attack it, the findings that were generated when the attack was successful. You can check this out today for yourself with a free trial of Security Command Center. Well, folks, thank you so much for following along with that demo. Always really fun to have the opportunity to attack something and show users what it really looks like in Security Command Center when we're catching bad things for users. To learn more, you can check out the link here, cloud.google.com/security command center. And I just want to thank you so much for coming to the talk today. My name is Tim Peacock. Thanks for learning about container threat detection. Have a great one.